Hydrostatics has much to be said about. The most important theorem of hydrostatics is the famous Archimedes Principle. You remember who was Archimedes? You know who Archimedes was? Was the first engineer on Earth, in opinions of many historians. He was a scientist working at Syracuse in Sicily, for the kingdom of Syracuse at the time. And he's famous for the principle, Archimedes Principle. What Archimedes Principle said? Maybe you remember. Any fluid which is submerged, which is immersed any solid, which is immersed in a fluid, experiences a force, a buoyancy force, which is called upthrust. In Catalan is empenta, in Spanish is empuje, hacia arriba, empente cap amunt, empuje hacia arriba. In English is upthrust. So every solid immersed in a fluid, addressed, the fluid being addressed, experiences an upthrust which is known. And it's exactly what? The weight of the fluid which is displaced by the solid. So if we just replace that part of the solid by fluid, and we compute that weight, then we can say that this solid, which has displaced that fluid, experiences an upthrust which is equal to that weight. So we know, if we know the shape of the solid, we know the density of the fluid. By multiplying the density of the fluid by this volume, we know the upthrust. Okay? Well, that is what is the known part of the Archimedes theorem. I have to say that this is not exactly the Archimedes theorem. The history, the legend says that Archimedes discovered something else in occasion of another problem. Did I tell you this is history or not, this story? Archimedes was working for the king of Syracuse. And the king ordered a new crown to the artisans and made of pure gold. This crown was of a complex shape. So at that time, computing the volume of the crown was very difficult. But they knew perfectly what was the density of the gold, the pure gold. Why? Because they could put pure gold, melt into a reservoir and then weight it and see the density. So they knew at that time which was the density of the gold. But why do I say this? I will tell you. Then the kingdom ordered this crown, so he gave to his artisans the pure gold, and after that he got back the crown. Apparently the crown was made of pure gold, but he was suspicious that it was not such a pure gold, that the artisans have mixed some pure gold with some silver to do the crown, which apparently look as pure gold, but they just kept some gold which was not silver, which was much expensive than silver, so they did some business with that. They were corrupted at that time already. So, but he wanted to not, he just was suspicious of that, but he couldn't prove it. And then he asked Archimedes to help him. So Archimedes, the problem of Archimedes was to know what was the volume of the crown. Because if he knew the volume of the crown, by multiplying this volume times the density of the pure gold, then it would know the theoretical weight of a pure gold made crown. And then by comparing this theoretical weight with the real weight, since the density of the silver is smaller, any mixture of gold and silver would have a smaller density and would have a smaller weight. But the point for him was detecting what was the volume of the crown. Okay? And they didn't have at this time enough knowledges of mathematics and techniques to determine the volume of complex shapes as the crown was. So what he did, he was, taking a bath in the bathtub. That was the sentence, no? And then he realized that putting something that, imagine that the bathtub, it was full of water, and then you see that when he introduces something into the bathtub, some water just, was spilled out, and then was displaced. Now, if he was able to put that crown into a completely filled recipient of water, that displaced water will just spill down, and then if he can collect this water and weight this water, he can compute the volume of the displaced water. And once, since the volume is the same, if he just submerged the crown, it could just see, or it could just, after this immersion, he could just obtain experimentally by weighting the displaced water what was the volume of the crown. And that's when he discovered that, and apparently he went out naked at the street saying, "Eureka, Eureka, I found it." Okay? So this is not, that's the story, that's the legend. That's not exactly the history, the one. But look, at the end, I don't know if it was Archimedes himself or some other, the problem was that he was able to determine the volume, and once determined the volume, we can postulate that the magnitude of the force is proportional, it's exactly the weight of this displaced volume. But, and with that I will finish, there is a second part of the Archimedes problem, Archimedes principle, which was that this force, where is this force, this upthrust force applied to? And the second part of the theorem of Archimedes says that this upthrust force is applied at the gravity center. At the gravity center of what? Of the solid or of the displaced fluid? The solution of the theorem says that this force is applied to the gravity center of the displaced fluid. So the complete Archimedes theorem says any solid immersed in a fluid experiments an upthrust force equal to the weight of the displaced fluid acting on the gravity center of the displaced fluid. Okay? So now we are going to prove that. The proof is very simple on the light of what we have seen so far. So look, first, we know that the fluid is at rest. So we know that according to that, the distribution of the stresses is hydrostatic. Now, if we consider what are the actions of the fluid on the solid through the boundary of the solid, of the immersed solid, of the submerged solid, that would be, of course, as an interaction, the product of the stresses times the normal. The stresses are minus P0 times 1 multiplied by the normal. That means that the forces are normal, and it consists of, it should be expected as a normal pressure equal to the hydrostatic pressure. Okay? But on the other hand, we know what is the distribution of this hydrostatic pressure. We already saw that this distribution is equal to a function which is a linear function in terms just on the z coordinates, assuming that the z coordinate is vertical with respect to the surface Earth, to the Earth's surface. So this is something that depends only on z, So it doesn't change as we keep z constant, okay? So that upthrust, the resulting forces on the immersed solid would be just the integral of all these forces on the boundary. Let's call it R, and let's call it the integral along the boundary of the immersed solid, and replace the expression. That's the expression, integral about the boundary, along the boundary, of minus P0 times n. This is the upthrust force. Okay? Now let's consider another problem which consists of replacing the submerged solid by fluid. So considering the same container without no body, no body immersed. Okay? So we replace, so to speak, the body by water. Okay? So what is the pressure distribution in this additional problem? Well, the pressure, since the pressure on the boundary that we are considering is just depending on Z, the distribution of pressures will be the same that in the original problem. So we can say that these forces here and these forces in that additional problem are the same. The P's, the pressures are the same. So the integral of the resulting of these forces in that case are equal to the resulting of the forces in the original problem which is what we wanted to compute. So that is something that I skipped. Now we are considering a homogeneous domain. So this is no longer the solid but the fluid. But the forces on the boundary of this domain, now the fluid domain, are the same than before in the solid. You agree with me? Okay. So now let's compute these resulting forces, and now we can apply the divergence theorem. Why? Because the divergence theorem couldn't be applied here, because that body was not homogeneous. This set was not homogeneous. But now we can apply the divergence problem because this is the distribution of pressure is now being continuous, because there are pressure inside, hydrostatic pressure. So now, and only now, that is a subtle detail, we can apply the divergence theorem here. So we replace n times gradient times nabla, and the integral on the body by the integral of the on the boundary by the integral on the interior of the boundary. So now we have that. Now we apply that equation. We replace this plus rho 0b. So finally, we obtain that the resultant of the forces applied on the boundary in the second problem, which are the same that the forces in the first problem, now can be computed as minus the integral of the boundary of rho 0b. B being what? The gravity forces on the fluid, because these are the gravity forces on this problem. Okay? So what is this? This is the weight. The weight of what? The weight of this portion of water, of fluid. So finally, we arrive to that conclusion. The resulting forces on this volume of fluid, which are the same that the resulting forces on this boundary of the solid, are equal to the weight of the displaced fluid, okay, times Ez, and vertical, in the vertical direction. So it's a vertical force whose modulus is the upthrust that we want to compute, and being that upthrust equal to the weight of the displaced force. So now we have proven this, that submerged solid experiences an upthrust force which is vertical and which is equal to the weight omega of the displaced fluid. So that's the first part of the theorem of Archimedes, the principle, Archimedes principle. Okay? Any question? Second part, we have just talked so far about what is the intensity of this force. That intensity is equal to the weight. But the resulting of these forces, so this resulting forces, these upthrust force, where is it applied? Is it applied in that position, or in that position, or in that position, or in that position? So we need to know where is this force is being applied to, okay, the resulting force. So that's the second part of the Archimedes principle. And look, this second part can be computed again in the same way. Look, with no loss of generality, let's consider that the origin of coordinates is placed at the center of gravity of the displaced forces, right? So that's something that we can do with no loss of generality. So, if we want to compute the moment of these forces with respect to the origin, now we have to take the integral on the boundary of the forces minus P0 times the normal times the position, vector of position of every of these forces. So that's the expression, okay? Since the moment of these forces are the same in the same problem that in the second, now let's consider that this is the displaced volume of fluid. Since the force at the boundary are the same, this doesn't change the problem. So this is the displaced volume of fluid with the forces exerted at its boundary and with the origin of coordinates placed at the buoyancy center, so the center of gravity of this displaced fluid. The expression of this is the integral on the boundary of the forces times the vector of position at every point. And now again, since this is a continuous problem, we can apply the divergence problem. So we replace the normal times nabla, okay? And we replace the integral on the boundary by the integral on the volume. So we do that. And now we replace, according to the fundamental equation of hydrostatics, we replace gradient of P0 by minus rho 0b, okay? So we replace that, and we see the following. The moment of the forces exerted on the boundary of the submerged solid is at the center of gravity at the buoyancy center, at the center of gravity of the displaced body. It can be expressed in that way. Minus the integral of the body of x being now the position vector of every point at this displaced water or fluid part, times rho 0b. Look, what is rho 0b? Rho 0b is the weight at every point of the displaced fluid. So, what is the definition of the gravity center of a body? The gravity, by definition, in the gravity center of a body is that place where the moment of all the weight, the forces, the resulting of the weighting forces passes to that point. Okay? So that moment, by definition, has to be zero, because that is the gravity center of the displaced body by construction. So we can say that this is minus the moment of the gravity forces, the center of gravity at the center of gravity, and by definition is zero. So this is also zero. So what we have proved? We have proven that the moment, the original expression, the moment of the forces exerted on the center of gravity of the displaced fluid, exerted by the outside fluid, which is the same than the moment of the forces exerted by the outside fluid in the immersed boundary, in the immersed solid, is zero at the buoyancy center, at the center of gravity of the displaced fluid. What does it mean? That these resulting forces, this upthrust force, passes through the buoyancy point. That's the second part of the Archimedes theory. So finally, we can say that the upthrust forces, these upthrust forces, passes through the gravity center of the displaced fluid, the center of buoyancy. Okay? So we have proven the two parts of the Archimedes theory.